So, we're about to dive in and really make sense of what some devs, probably most, see as weird behavior in CSS. And the goal is that you can spend less time troubleshooting and more time building. So, as I already mentioned, we do have a lot to cover. So, we're going to get right to it with our first key concept, which is how CSS computes in the browser. Now, a high level understanding of how CSS computes in the browser is quite useful in helping us learn why CSS is the way that it is. There are essentially four phases to how the browser approaches styling CSS. The first one is style computation. And this is where the browser examines the DOM and works on assigning a value for every CSS property that exists. So in order to do this, the browser first completes selector matching by compiling a list of all style rules that are eligible matches by traversing a tree of nodes based on relationships between parent, children, and sibling elements. Then it evaluates competing selectors and picks the winning property through rules of the cascade. Next, it's going to compute final values by absolutizing lengths. For example, turning 1FR in this grid definition into a pixel value. Then it will fill in missing property values with either the inherited or initial values, resulting in one value per applicable property per element in the DOM. The next phase is box construction. And so with each property filled with a final absolute value, it's time to construct the box for each element and pseudo element. This particular thing was something I kind of knew from working with CSS, but I didn't really understand. And so what happens here is that every DOM element may have 0, 1, or 2 boxes constructed based on these criteria. So we get 0 boxes constructed by using display none or display contents. And 2 boxes are created for tables, which include the box that encompasses the table and an outer principal box for a possible caption. And we also get 2 boxes for list items, which includes the outer principal box and the marker box. And 1 box is created for all other display values. Now, beyond these physical sorts of boxes or non-existent boxes, we also have concepts for runs of text. So runs of text without a containing element may receive an anonymous box. And this happens when the text is a child of a flex or a grid parent, or the text shares a container with block level siblings. Anonymous boxes cannot be directly styled because there's no target element for a selector to act on, but they can inherit styles from a direct parent for styling purposes. Now, you've likely dealt with inline anonymous boxes most frequently, as those are created around text within elements such as a paragraph, when it also includes an inline element sibling, such as an M. Each line of text is also contained within line boxes. Now, there are a few more definitions to go through if we had time, but this is kind of a good set to start to get familiar with. The third phase for the browser computing our CSS is layout. And the layout phase is when each box's size and position is determined. So the size and position is calculated in part by looking at where the element sits in the DOM tree, including its parent, next and previous siblings, and its child content. This includes examining the DOM and style data for content and style context. The work for evaluating size and position is complete when the browser has a value for the X and Y positions and a value for the width and height. Finally, after every property has a calculated value, boxes are constructed and the layout and size and position is determined, the browser paints the visual display to the screen. Now, simplified, The painting process begins at the top left corner, where the browser recursively draws and places the children within each container before drawing and placing the container. This is repeated for each successive element in the DOM. Paints occur not just on first load, but whenever visible style changes occur, such as modifying a background or assigning an outline. Now, that was a lot that's going on in order to render styles for our CSS. And impressively, at least I think, it typically happens in a few hundred milliseconds or less, except in outstanding cases, such as when pesky JavaScript gets in the way. Now, our next key concept is stacking context. And now that we've learned how browser comes together, or CSS comes together in the browser, let's look at this rendering concept that is often a source of frustration for developers. The stacking context defines the order things are placed in the third dimension, or the z-axis. If you've used z-index, then you've worked with stacking context. We can think of the z-axis as layers of DOM elements between the root of the stacking context within the viewport and you, the user, looking through the browser viewport. Stacking context also comes into play when dealing with multiple layers of elements that are treated as overlays, such as sticky navigation, dialogues, modals and panels, and tooltips. Stacking context also affects situations such as absolutely positioning an element within another component. So, what creates stacking context? Most commonly, you'll end up with a new stacking context from using a fixed or sticky positioned element, or combining position absolute or relative along with z-index. Interestingly, container type inline size or size also creates a new stacking context, which is useful to know if you're starting to use container queries. Use of z-index also leads to new stacking contexts when applied to flex or grid children, and to perhaps surprising properties that create a new stacking context are opacity with a value less than 1 and mixed blend mode. I definitely encourage you to go out to MDN, check out the full list of conditions for creating stacking contexts, because there are a few others that can surprise you. So our key concept is, how do elements stack, now that we kind of understand what a stacking context is? So let's take a closer look. Once a stacking context is defined, children become part of the parent stacking context. And nested stacking contexts result in a hierarchy of stacking contexts. Is anybody playing bingo with how many times I'm saying stacking context? So when a z-index isn't set, elements are stacked according to DOM order once they receive a positioning property. This means that elements that come later in the DOM may be stacked above elements that come earlier in the order. For example, a relatively positioned element with top -20 pixels and no z-index will appear stacked on top of previous elements. Changing the layering order with z-index allows moving elements above or below other elements within the same stacking context. So here's our real key takeaway from all this talk of what a stacking context is. And that is that an element can only be relayered within the same stacking context. So if you've ever tried to raise an element to the top using a high z-index, 9999999, and didn't have success with that, it's because the element you were raising and whatever was still above it were in different stacking contexts. So for an example, you may have a tooltip that you want to place above an icon button, but it appears to be overlapped by a sibling of the tooltip's parent container. In that case, the sibling likely sets a new stacking context, which prevents the tooltip from visibly being layered on top. So to ensure components like tooltips appear above everything else without being affected by stacking context issues, some frameworks portal those components to the end of the body. And in addition to applying usually a large z-index. This works because being last in the DOM order places it in the outermost stacking context. And coupled with that Z index, it reduces the likelihood of layering conflicts from siblings. Portaling allows authors to instantiate the component close to a trigger, but escape the potential stacking context pitfalls. Now, we are going to shortly look at a more modern way to manage this type of issue. A property created for the explicit purpose of creating a new stacking context is isolation. And isolating an element has the practical implication of creating a stacking context without any other layout side effects. It doesn't require an additional position property or z-index to work as a new stacking context. So one way to prevent isolation or to use isolation is preventing a child element with a negative z-index from seemingly escaping the parent and disappearing behind the parent's background. So let's go ahead and take a look at our first demo here. So here we have a post with a number that we want to become part of the post background, kind of like a watermark. And you may be able to tell that currently that number is appearing above the text. So let's try to move it behind by adding a negative z-index. And that hasn't quite worked, right? Because the post and the before element are currently part of the same parent stacking context. So instead, we need to create a new stacking context so that the parent post element can contain its children and any stacking context that they create. And this is where we add isolation isolate, which solves the problem by creating a new stacking context that the before can no longer escape. Now the number is slotted behind the text due to the negative z-index, but in front of the post background. Cool. So moving along. Remember how I mentioned there was a better alternative to portaling overlays to avoid stacking context conflicts? Well, the modern web solution is the concept of the top layer. And the top layer is guaranteed to be the topmost layer above any other stacking context. It spans the entire viewport, although its elements existing in the top layer can have smaller visible dimensions. Promoting an element to the top layer breaks it free of any stacking context it may otherwise exist within. Currently, there's not a CSS property to assign an element to the top layer, but rather it's used in the following context. Full screen elements that are triggered from element request full screen, think of video in full screen mode. The dialog element, specifically when used with the show modal, and also popovers. Now, the last method of popovers is a new concept as of 2023. It's currently gaining browser support. I forgot to double check if it's landed in Firefox. So if anybody knows or wants to run over to Can I Use, let us know. But it's a way to instantiate a wide variety of overlays, such as tooltips, panels, or menus via HTML attributes or JavaScript. So without the need to define a stacking context or deal with z-index, popovers will exist in the top layer, which automatically promotes them above other content. A related CSS spec for anchor positioning is also in progress, and that will help you dynamically position popovers and other content. And at the conference that this was originally presented at, Hidda DeVries has been giving a excellent talk on popovers. I think it's recorded and out there. Please go look that up and you learn a lot more about popovers, especially if this is the first time you're hearing of it. All right, so our next key concept is how the browser does value calculation. And as we reviewed for the style computation phase, the browser's goal is to calculate one value per property per element in the DOM. Something you learn early on about CSS is that you can change a property's value multiple times from multiple values that may select the same element. Each of these are declared values. And due to specificity and the cascading order, The element's final selected value may be the cascaded value. If a property does not receive a value from the cascade, then it will use either the inherited or initial value. The inherited value comes from the nearest ancestor that has assigned a value. And that's only if the property is allowed to inherit, which includes properties like color, all the font properties, and text alignment. Initial values are used when no inherited value exists or is allowed, and are the values provided by the specification for the property. So in other words, the defaults in the user agent. Some property definitions require further computation to absolutize the values. These transformations result in the computed, used, and actual values, which refer to the progressive steps that may be involved to end up with an absolutized value. Some value transforms that may occur include relative units such as VW, ems, and percents being converted to pixel values, and floats may be converted to integers. Current color and other named colors like Rebecca Purple are converted to an sRGB value. And also, there may be compositing values that affect each other. For example, a definition of padding 1em requires computing the value for font size that em depends on. And custom properties are replaced with their computed values. Now for this demo, we're going to take a look at the Computed tab in Browser DevTools to discover the absolutized value. So in our code sample, we're using all kinds of values, none of which are already considered absolute. The browser will have to do the computation on each of these on top of making sure that these are even the final values to be used. So I'm going to go ahead and open up DevTools and we'll inspect a few things here. I'll bump up the font size a bit. Great. So if we just pick a property here, we'll pick our font elements here, text elements here. I'm going to flip over to the Computed tab. So I've selected a paragraph. I'm going to go to the Computed tab. And of course, we can see all sorts of values in here. But for example, our font size, which uses clamp to adjust the font size, you can see this value changing currently if I change the size of the window. And by the way, you can filter these down, which is useful when you're inspecting something in particular. So you can keep that kind of visible. And some of you may have noticed that this font size actually is also sneaking in another new property, which is the use of container query units. But currently it's not responding to its parent container. Let's fix that real quick. That's going to also adjust how this property is computed. So just real quick, we're going to make the post container the post parent a container. And now that font size is actually using the container query inline value. But either way, it's pretty useful to pop into Computed and see that in fact, the browser is converting what otherwise would be a rem value interpolated with that container query unit into a final pixel value. Now, in a related way, we can check out some of the other properties like the width, which is using the min function. And we can see that adjusting as well. It's kind of interesting to understand how these values come together and how the browser is actually interpreting them. All right, let me close out of that. So that brings us to our next topic about kind of what happens in a sort of special computation scenario. And it has a pretty critical impact on modern CSS. This is the concept of computed value time, which exists when the browser assigns values to custom properties. As described earlier, typically unfilled and invalid property assignments will fall back to cascaded values when applicable. This is great. We love this journey for the cascade. However, Custom properties are not able to fail early in terms of realizing the value may be invalid. So they'll either use an inherited value from an ancestor or the initial value for the property. Critically, this means that invalid custom properties are unable to fall back to a previously set cascaded value, as you may expect, because those have been discarded from the decision tree. So that means that in this example, the card paragraph will be the inherited value of red as provided by the body. It's unable to use the cascaded value of blue due to the browser discarding that as a possible value candidate at computed value time. It's only when the user agent attempts to apply the value that it realizes it is invalid. Now, all hope is not lost. So if later a utility class on the paragraph were to update the color property, then due to rules of the cascade and specificity, it would win out like normal, and the invalid custom property value would not have an effect. Now, note that when referring to invalid values for custom properties, that what makes it invalid is how it is applied. So, for example, a space character is a valid custom property definition, but will be invalid when applied to a property. On the other hand, a custom property with a value of 100% may be applied to width, but would be invalid applied to color. Another scenario where a custom property being invalid at computed time may break your expectation is using the custom property as a partial value or undefined with a fallback. So given this rule for an H2, you may expect that when the CQI unit is not supported, the browser will simply use the prior font size definition. Instead, the browser comes along, assumes it will understand the second clamp definition, and discards the prior font size definition for H2. But when it goes to populate the custom property value and finds it doesn't support CQI, it's too late to use what is intended as the fallback definition. This means it uses the initial value if there is no inheritable value from an ancestor. Okay, pop quiz. While you might think that the initial value would be a font size befitting at least the H2 level, does anybody know what the actual initial value is for font size? You have a guess of 1 rem? I think that is a reasonable guess. So according to the spec, the initial value for any element's font size, so regardless of the heading level, is medium, which is in fact typically equivalent to 1 rem. Now, because of this, in this scenario for our H2, that means we not only lost our intended fallback style, but also the visual hierarchy of the H2 in browsers which do not support CQI. Now, this is an issue I got burned on. I didn't follow my own and also the standard advice of be sure to cross-browser test, and had to real quick learn about this concept to update an article that I published a while back. So yeah, look out for this one. And confusingly, browser dev tools for the unsupporting browser may still show the failing H2 rule as being the applied style. So that can make it extra difficult to troubleshoot issues caused by custom properties being invalid at computed time. So for this demo, we're going to look at an alternative solution to the previous issue and look at wrapping that definition in an @supports so that unsupporting browsers actually do use the fallback. So let's check that out and do that. All right, so here's the setup that we know will not work as intended. So what we'll do first is remove the definition that uses the CQI unit. Then we'll adjust the custom property name to specifically say it's the fallback. And let me adjust the window here. So you can see the whole definition. There we go. And now we can create an @supports rule to check for CQI support and place the upgraded H2 definition here. We can now be sure that our fallback will be used in browsers that don't support CQI, and that our solution will be upgraded when CQI is in fact supported. By the way, I did spin out kind of that section into an article on moderncss.dev, which I mentioned because that was a lot of detail to take in. You can explore those demos yourself, poke at them in DevTools, and hopefully better understand that concept of invalid at computed time. Cool. So our next key concept also is around custom properties, but specifically inheritance. So calculation of a custom property value is performed as soon as it is found. Then the computed value is available for inheritance. A common convention is batching custom properties into the root selector. And if one of those values involves a calculation based on another custom property, the modifying property cannot update the calculation later. This is because the calculation happens as soon as the browser processes the definition against the root, essentially because it assumes there's no further rules to process. So a static value is produced, which is inheritable but unchangeable. If we lower the custom property calculation to be applied based on classes, then the browser will be able to recalculate as part of the value processing to determine the computed value. This is because it will calculate a value for elements with the class of font resize and a separate value for elements with both the font resize class and font large class. Now we'll review kind of a few weird ways the browser paints certain properties and how that affects the box model and element interactions. When dealing with designing box styles, it can be useful to understand the paint order of certain properties. Might be another concept you've worked with your entire CSS career but haven't ever really thought about. So here's the applied paint order from the bottom of the paint stack to the top. The bottom is the outer box shadow, then background color, a background image, box shadow with inset, border, and finally outline. And a couple more notes are that a box shadow which is not inset is painted outside of the border box, which means it will not be visible beneath an element with a transparent background. And the shadow will render beyond the perimeter of the border, but underneath the outline. All right, here's our second and last pop quiz. Which box properties do not accept event listeners for an element? All right, so the properties that do not accept event listeners include box shadow and outline, but they will trigger once inside of the border. So in some cases, this means a user has to move further inside of the element to interact with. So if you think of a technique such as using multiple box shadows to add the appearance of extra borders, this is a scenario where that may actually impact the user experience. Now there's a few unique aspects of background rendering, including that background colors and images will extend under the border by default. And this can be adjusted by setting background clip padding box, which clips the background to the outer edge of the padding and prevents it from being painted in the border space. I'm just going to flip back to the previous one to see the difference. So it's underneath the border, and now with background clip, it's inside of the border. The default is border box, which is why it's initially allowed to extend and cover the element. Two other default behaviors of background images, which include gradients, is that they're confined to the content box. Background images are also initially positioned relative to the content box. The feature for managing the painting of the background is background origin, which directs where to begin painting the background. Use of the border box value, as seen here, allows gradients to cover the elements, as shown. And the difference between background clip is that with background origin, any overflow is not prevented from being visible under the border. The background origin property also affects the offset location of the background position, which is defaulted to content box. And this is to prevent borders overlapping a background image. Now, this section is even just to like verbalize it, it's kind of confusing. But I find that background clip and background origin, those are definitely two weird properties that I only look them up when I need them. I can never remember what to type in to get to the right solution. So hopefully this puts that little nugget in your brain as well when you need to search for how to handle these sorts of scenarios. Okay, almost done. I couldn't end a presentation without flipping us forward and looking at some modern CSS things that smooth over some of the weird things we have been dealing with in CSS. All right, so the first one is a celebration, at least to me, which is evergreen browsers now support outline following border radius. And this was true across browser as of Safari 16.4, which we got, which was released in March. Also, in case you missed it, this one's a little harder to miss, but defining an aspect ratio is now as easy as the single dedicated property of aspect ratio. The syntax to define the ratio is a / separator. So for an HD video, you would write aspect ratio 16/9. And for a perfect square, you can simply use aspect ratio 1. Now, you may safely use aspect ratio without worry of content overflow because the ratio is forgiving and allows content size to take precedence. So unless you also have dimension properties that limit the element size, the aspect ratio will allow content to increase the element size. One of the newest properties that was being developed in Chrome, I believe, I should have updated the support here. I think it's now out in Chrome at least, is text wrap, which has two values that solve the typesetting problem of unbalanced lines. The first available value is balance, and this has a goal of evening out the number of characters per line of text. There is a limitation of 6 lines of wrap text, so it's best to use on headlines or other shorter passages. And it also, when we limit the scope, it also helps limit the impact to page rendering speed. The other value is pretty, which specifically addresses preventing orphans and can be a little more broadly applied. The algorithm behind pretty will evaluate the last 4 lines in a text block to work out adjustments as needed to ensure the last line has 2 or more words. Now, this is an excellent example of a progressive enhancement where if it works, that's great, but there is one side effect to be aware of, which is that any adjustments do not change the computed element's width. Now we know what that means. So a side effect in some layouts may be an increase in unwanted space next to the text. Styling list markers is also now super easy. So we're talking about the bullets of an unordered list or the numbers in an ordered list. And this is now possible with the marker pseudo element. This selector has access to a limited set of properties, but one that solves a long-standing weird issue is being able to change the color property. So we finally can have the marker be a different color than the list item text. And last, but certainly not least, again, if you somehow missed the buzz, the long requested feature of the parent selector has arrived in CSS. Using has allows selecting a parent based on checking what children it contains. But we can also check for certain sibling conditions using combinators, like this one, which selects the H1 if it is followed by an H2. We can extend this idea to select elements that come before another condition, like selecting list items prior to a hovered sibling. A really powerful use case is creating quantity queries by selecting an element with a certain number of children. With nth child, in the first example, we're selecting a grid that has at least 5 items. And in the second example, we are combining with nth child with last child to select a grid with exactly 5 items. And hopefully that's enough of a taste of has to get you excited to learn more. All right, so I hope you feel a little less weirded out by CSS, and you can always find me to nerd out on these topics and more. So thank you for having me.